My name is Shilpa and I'm presenting the paper Performance Evaluation of Cuffless Blood Pressure Estimation Methods using Linear and Non-Linear Models with PTT and PR parameters. This is the outline of the presentation. And first of all, BP, blood pressure, is the measure of force or pressure exerted by the blood on the arteries as the heart pumps blood through the body. And generally, it is represented by systolic and diastolic BP values. Systolic BP is the pressure when the blood in the arteries, pressure of the blood in the arteries when the heart contracts, whereas diastolic BP is the pressure of the blood in the arteries when the heart relaxes between the heartbeats. And using the BP readings, we can categorize the blood pressure values into hypotension, normotension, and hypertension. So for hypotension and hypertension, these are linked with various health issues such as heart diseases, stroke, kidney failure, diabetes, sleep apnea, etc. So this highlights the importance of BP monitoring in daily life. However, for BP measurement methods, we have it is categorized into two, which is invasive method and non-invasive method. In invasive method, we are inserting a catheter into the blood arteries and measuring the BP, which of course has many challenges because it has to be done in an office, like hospital setting under supervision, and also there is chance for blood clotting and other health concerns. For non-invasive method, the traditional method that we use is cuff-based, but it does not ensure the continuous BP measurement. So for cuffless BP monitoring devices, it enables the continuous measurement of BP in real life without any disturbance. So in the literature that we what we found out is that the blood pressure has high correlation with the PTT and PR. The PTT is the pulse transit time, which is the time difference between R peak of the ECG signal and the systolic peak of the PPG signal. So once we have this ECG and PPG signals, we can calculate the blood pressure. We can estimate the blood pressure from these two signals by using PTT and HR as variables. So the major objective of the work is to implement the linear and non-linear models for cuffless blood pressure measurement using PTT and PR parameters for accurate and reliable ambulatory BP monitoring systems. And also we employed RLS, which is a recursive least squares algorithm, to estimate the SPP, DBP, and MAP values. And we also presented an approach to ensure the reliability of SPP and DBP measurements by comparing the error between the estimated BP, which is MAP-E, and computed MAP-C from the measured SPP and DBP, which I will be discussing further in the coming slides. And also the performance of the BP estimation methods is evaluated using the MIMIC database in terms of mean absolute error, Bland-Altman ratio, and BP estimation error range metric. So first of all, the linear BP estimation model. First of all, the MAP is defined as 1/3 SPP and 2/3 DBP. Now, in order to find, in order to define a linear model, what we are doing is that we are characterizing SPP, DBP, and MAP values as a function of PTT and PR values. So we get a system of linear equations, SPP, DBP, and MAP as a coefficient matrix into the input matrix, which is PTT and PR values. So Y is the output matrix which contains the BP values, and X is the input matrix which contains the PTT and PR values calculated in each cycles, and theta is the coefficient matrix, calibration coefficients, which is specific to each subject. Similarly, we are defining a nonlinear BP estimation model also. Here we can see that the only difference being instead of PTT, we are taking a logarithm of PTT. Other than that, everything is same. So here also we are defining the input matrix, coefficient matrix, and output matrix. Now we are employing the recursive least square algorithm for BP calibration. Here, here we are calculating the coefficient matrix iteratively as given by equation 9 it is find out in such a way that it minimizes the cost function of L2 norm of the square of L2 norm of y minus x into theta. And we are for every recursion, every iteration we are updating the correlation matrix Pn and coefficient matrix theta n, and Pn and theta n are updated in each like iteration using the equations P11 and 12. And here lambda is the forgetting factor that provides the weightage to recent measurements. Now, in order to validate the database, in order to validate the performance, we are using the Mimic database, which is available in the Physionet website. It contains 72 records having clinical data extracted from more than 90 ICU patients, and it has sampling frequency of 125 Hertz. And here only 35 records contain a complete set of ECG, PPG, and ABP signals, along with the annotated ground truth information. So once we got the ECG and PPG signals, what we are doing first is passing it through high-pass filter for baseline filtering. And now what we are trying to do is that in the annotations that is given in the database, which is represented by this black circles, we can see that it is not exactly on the peak. If it is on the peak, we can calculate the PTT as a PTT and pulse rate from this peak annotation locations. But if we are having the onset locations, we have to find out the actual peak locations from the given locations, onset locations. So what we are trying to do here is we are taking the 200 millisecond window from the given annotation, which is given by this black circle. We are taking 200 millisecond window and finding the local maximum. Then we get the original like R peak of the ECG. Similarly, we are doing for PPG also. We are taking 200 millisecond window from this given annotation and finding out the local maxima, and we get the systolic peak location. Once we got both R peaks and systolic peaks, then we can calculate the PTT as the difference time difference between the R peak of the ECG and systolic peak of the PPG. And also RR interval we are calculating as the difference between consecutive R peaks. So this RR interval is essential for calculating the pulse rate. Pulse rate is inversely proportional to the RR interval. Now we are doing the calibration and testing. For calibration, we are using the down truth SPP and DBP values. Calibration coefficients were calculated by employing the RLS algorithm for initial minute of data. The calibrated coefficients are then used for prediction of SPP, DBP, and MAP values using the both linear and non-linear models. For 1 hour, we are doing the estimation. Now, in addition to the predicted MAP values, we are also calculating the MAP values using the estimated SPP and DBP values. Now, if you look at the results here, you can see that here figure 3 depicts the reference and estimated BP values for record 253. Red indicates the original value, and blue and black indicates the linear and non-linear estimated values respectively. And this is for record 041. Similarly, we are plotting for entire 35 records, the original and estimated values. And then we are evaluating the performance of these BP estimation models, linear and non-linear models, in terms of standard performance metrics such as MAE plus or minus ST, root mean square error, blind Altman ratio, etc. So here we can see the linear and non-linear models are almost similar, giving performance almost similar. But the problem is, if you look at the standard deviation, it is very high. So that means that we have to further investigate the reason behind this poor performance. So for that, we thought estimation error range table will be a better metric for evaluating each record individually. So these 5 records, we are plotting tabulating the estimation error range table. Here we can see that for 0 to 2, 3 to 5, 6 to 10, 11 to 15, and greater than 15 error. We are finding out the number of cycles within each of these ranges. So for these 5 records, we can see that for error greater than 10, only few number of cycles are there. So these 5 records are performing satisfactorily. And if we tabulate the performance of PP estimation models for other 30 records. What we find out is that this for greater than 10 mmHg error, we are having more number of cycles. So we further investigated the reason by visually inspecting each of the record, each of the signals, ECG, PPG, and ABP. And what we found out is that during the initial calibration, if the signal quality is very less, then we cannot find out the PTT and PR values properly. And similarly, we cannot find out the calibration coefficients also will be not proper, not optimum, and also we will get the poor estimation results. Similarly, also in some records we can see that some portions are 0, but the BP values are not 0 in the ground truth itself. So this also creates some kind of error, and also in the testing duration also the signal has to be good enough so that we can calculate the PTT and PR values properly. So for each records, we are calculating this. We are finding out the results for reasons for large PP error, and we gave it in a table here. And here the conclusion is basically we studied the performance of calibration-based non-invasive cuffless linear and non-linear BP measurement models with PTT and PR parameters extracted from the ECG and PPG signals. And the map values estimated from the linear and non-linear models were compared with the map value computed from the corresponding SPP and DBP values for ensuring the reliability of the SPP and DBP values. And also this study highlighted the importance of signal quality assessment for accurate calibration and reliable PP estimation. And also it emphasized the need for an accurate detection of the R peak locations in ECG signals and systolic peak locations in PPG signals for reliable PTT and PR measurements. Then only we can find out the accurate BP measurement using these PTT and PR values. So this research work was carried under Indian Council for Medical Research. And these are the references that I used.